All right, welcome to Physics Essentials video 5.1. We're going to be learning about gravitational and electrical forces. So here's your objectives. By the end of this video, you should understand that gravity is a force which pulls any two objects together. You should understand how the force of gravity is affected by the mass of the two objects involved and the distance between the two objects. And then for electricity, you should understand that electricity is a force that either pulls the two objects, two opposite charges together, or pushes two like charges apart. And then number 4, you should understand how the force of electricity is affected by the charge of the two objects and the distance between them. Finally, number 5, which I should have added here, is this. You need to be able to explain to me how we know these two forces need to exist. At the beginning of the video here, I'll talk about Newton, which is kind of who made this realization about gravity. I wouldn't say he discovered gravity, but he made this realization that gravity pulls any two objects together. All right, and then we can follow a similar train of thought for electricity, and we'll talk about that at the end of the video. All right, so anyway, here we go. Let's just do this. So, Newton and the apple. So, as the legend goes, one day Newton was hanging out and having a picnic or whatever under a tree. So here you can see, Newton is hanging out. So maybe here's his picnic blanket, right? And he's got a milkshake or something, right? Because Newton loved his milkshakes. And as he was drinking his milkshake, an apple fell down out of the tree and knocked him on the head. And so he started thinking about this. He's thinking, okay, well, gravity pulled the apple down onto my head. So as he was doing this, he was looking up into the sky and he could see the moon. And he was thinking to himself, all right, well, gravity pulled the apple down and it, hit me on the head. Well, back in those days, they viewed the moon and the sun and the stars as sort of heavenly objects, and they didn't follow the same laws of physics as things on Earth did. But as the story goes, when the apple hit Newton on the head, it occurred to him, well, maybe gravity does affect the moon the same way that it affects the apple. All right, so here's what he began visualizing in his head. He's thinking, all right, well, I know, because I'm a smart dude, that the Earth is orbited by the moon. Oops. All right. So he's thinking about this. And so he begins thinking, and he knows, because it's his first law, that if an object is in motion, it wants to stay in motion. So if the moon is right now moving this way, and there are no forces on it, it's going to want to keep moving that way. And he had never thought about it this way. And what he came to realize was, well, wait a minute. If there's no force on the moon, it's an object just like that apple is. So if there's no force on it, it should just keep moving and follow this line over here. And he said, wait a minute, there's got to be a force acting on it. And that force is the same force that pulls this apple down over here. Gravity pulls the apple down in the exact same way that gravity pulls the moon inward and prevents it from floating away from the Earth. And, this was a big discovery, that all objects behave following the same set of rules, okay? And that the rules that describe how the moon moves are not any different than the rules that describe how the apple moves. All right. So then he started thinking, well, so what makes the Earth so special? Why is the apple and the moon and everything attracted by the Earth's gravity? Why does the Earth have gravity and other objects don't? And he realized that that wasn't the case, that every object has gravity. That's a little bit sloppy, but so here's what he realized. He realized that any two objects in the universe are attracted by a force of gravity, okay? And that force of gravity depends on these things here, okay? The force of gravitational attraction. This force of gravitational attraction we're going to abbreviate as FG, right? Force of gravity, force of gravitational attraction. And what it depends on is the mass of the two objects. So the more mass each of the two objects has, the larger the force of attraction is between them. And it also depends on the distance between the two object centers. Okay, so the closer the objects are together, the larger the force of attraction between them is. All right? So let me stick a slide in here and kind of give you a little bit more of a visual here. So check it out. If you've got any two objects in the universe, whatever, here it is. Here's object A and object B. All right? In the same way as if these were magnets and magnets would pull each other together, gravity works kind of the same way. The idea is both of these objects have mass. So there's the mass of object A and the mass of object B. And because those two objects have mass, they attract each other with a force of gravity, right? Remember, those two forces are equal, right? This force here is the force of object B pulling A, right? Newton's third law tells us that there's an equal and opposite force of A pulling B. All right? So those forces are equal. Now, how much force there is depends on the mass of the two objects and the distance between them. All right? So if you make either of these two objects bigger, if you make either the mass of A a bigger number or the mass of B a bigger number, it makes the force of gravitational attraction between them bigger. Okay? And there's an inverse relation with distance, which is that as your objects get closer together, then your force gets bigger. Okay? Which is what all of this says. All right? The red tells us about the mass, and the blue tells us about the distance. And then the green down at the bottom is the reminder that the force is equal on both objects. Okay? So this all seems a little bit counterintuitive. It's probably easiest if we think about this example here, which is this. Your weight on Earth is an example of a force of gravitational attraction. All right, so check it out. Let's pretend for a moment that you and the Earth are the only two objects. So here's the Earth. Earth. All right, and here's you. Hello. And you're drinking a milkshake because you like milkshakes. We have agreed that gravity is pulling you down, right? Now, when we say gravity, what we're talking about is the Earth's gravity. So here's the force of gravity from the Earth. Remember from when we did Newton's third law, we said that the action force was Earth, or Earth's gravity, pulls you down. And then the reaction would be you pulling the Earth up. That's also a force of gravity, right? So you, technically it's your gravity, pulls the Earth up. And those two forces are equal. The only reason we don't notice the Earth moving is because it has such a big mass. All right? So what this tells us is that there are three ways that we could make this force of gravity. Remember, weight is force of gravity. There are three ways you can make that force of gravity bigger. Okay? One way would be to make your mass more, right? You know that if you go home and eat a whole bunch of donuts, you gain mass, and so you gain weight, right? So that's one way you could make the force of gravity bigger. It turns out if the Earth's mass was bigger, you would weigh more, right? We talked about that. If you go to Jupiter, you weigh more, right? Because Jupiter's a bigger planet. So if the Earth had more mass, you would weigh more, okay? And then finally, the other way you could change your weight is if you could somehow get closer to the Earth's center. This becomes a little bit weird, so it's probably a little bit easier to say that you'd weigh less if you moved farther away from the Earth's center. It turns out that when you stand at the top of Mount Everest, that's Mount Everest, if you stand here, you actually weigh a little bit less because you're now farther away from the Earth's center, as opposed to when you stand just, you know, in Detroit. Okay? So there you go. So let's talk about electricity. In order to do that, in order to learn about electrical forces, we need to talk about what's called charge. It's pretty simple. All objects are made of atoms. You know that. Atoms, you may or may not know, are made up of three types of tiny particles. All right? Those three tiny particles are called electrons, neutrons, and protons. All right? And it turns out that two of these particles have what's called charge. Electrons have what scientists call a negative charge, and protons have what's scientists call a positive charge. And then neutrons actually have no charge at all. They're not positive or negative. They're just zero. Okay? So, electrons, neutrons, and protons, in addition to having mass, also have this thing called charge. Or I guess neutrons don't, but all right. Now, it turns out that most atoms have an equal number of electrons and protons, and as a result, the amount of positive from the protons and the negatives from the electrons cancel each other out. So most atoms don't have any sort of overall charge. However, sometimes an atom can become what's called ionized. You don't necessarily need to know that word, but that means that it has either gained or lost electrons. Okay, so if that happens, if you've got, say you've got 10 protons, right? A usual atom will also have 10 electrons. But if you gain electrons, then your positives and negatives don't cancel out. Similarly, if you lose electrons, your positives and negatives don't cancel out. All right, so in that case, the atom and the object the atom is a part of will gain either a negative or a positive charge, and so then we say that it is charged. Okay? So, that's the deal with charge. You guys have all seen charge before. If anytime you get a shock, you touch somebody and you get that little shock. If you rub your feet across the carpet, sometimes you feel it. That's all just built up charge. Sometimes on old computer screens or old TVs, if you've got an old non-flat screen TV, you might feel that static built up on the screen. That's also charge, okay? So electrical force, which we're going to call Fe, works a lot like gravitational force. And here's the two biggest differences. Number one, gravitational force depends on mass, right? We talked about that. Electrical force depends on charge, okay? Charge is something that can be measured in the same way that mass is. You can measure mass in what are called kilograms. You knew that. Charge is measured in what's called coulombs. We'll talk about that more later on if there's time. All right, so that's the first difference. The second difference is that gravitational force always attracts two objects, right? If this is you, no, if that's the Earth, and this is you, gravity is going to attract you, right? Electrical force can either attract or repel, all right? It'll attract the two objects if they have opposite charges. So if you've got an object with a positive charge and an object with a negative charge, then the force of electricity will attract them, okay? Whereas if they're like charges, this is the second part down here, if they're like charges, if they're either both positive or both negative, then the force of electricity pushes them apart. Okay, this is actually a little bit, I talked about magnetism before, this is a little bit more like magnets. You guys have seen this before where you can set your magnets up so that they pull each other together, like your Thomas the Train set where the cars attract each other, right? But sometimes you can flip the magnets around and get them so they repel each other, okay? And that's kind of like what goes on with like charges for electricity. All right, so from there, this next slide is the same as the gravitational one. The force of electricity depends on the charge of the two objects, all right? The more charge each of the objects has, the larger the force of attraction or repulsion is between them. And then it also depends on the distance between the two object centers, all right? The closer the objects are together, the larger the force of attraction is, okay? All right, and just like with gravity, the force of electricity is the same on both of the two objects, all right? So finally, how do scientists know that the force has to exist? Well, it's the exact same way that Newton knew that gravity had to be pulling the moon inward, right? Check it out. An atom looks like this. It's got a nucleus, all right? And the nucleus is made up of neutrons, which doesn't have a charge, and protons. So the charge of the nucleus of an atom is positive, all right? And here's your electron. Electrons are negative. And in an atom, the electrons, in the same way that the planets orbit the sun, electrons orbit the nucleus of an atom. This is a terribly inaccurate drawing, but it gets across the idea that the electrons orbit the nucleus. And so, for the same reason the moon didn't float away, right? Gravity pulled it in. Scientists said, well, the electrons, something has to be preventing the electrons from floating away. It turns out there's not enough gravity. There is gravity here because these both have mass, but that force of gravity would not be enough to prevent the electrons from floating away. And so there must be another force, and the name of that force is electrical force. All right. There's a lot in this video here. We will make sure that we talk about this in class and kind of clarify some of this stuff. For now, the big things that you need to understand are those objectives that I put at the beginning of the video, and make sure that you have copied down the force of electricity, what it depends on, and then same thing for the force of gravity slide. Back here. All right. Those are, I would say, the two most important slides. All right. Hopefully you got it all down. I'm going to stop now because I imagine I'm getting close to 15 minutes. Look at that. All right. Have a good day.